In this podcast, we're going to be reviewing the graphs of polynomial functions. Right? So general polynomial formula, p of x equals a subscript x to the a subscript n x to the n plus a subscript n minus 1 x to the n minus 1, and all the way till you get to the constant term. So in other words, when we're in standard form, our highest exponent goes first, and then one less goes next, unless of course that has a coefficient of 0, in which case we don't have to write that in, and so forth. Okay? N is the degree of the polynomial, so whatever the largest exponent is, that's your degree. Your standard form is for descending powers of x. A subscript n x to the n is said to be the leading term. So the leading term is the term with the greatest the greatest exponent. So whichever term has the greatest exponent, that's your leading term. And so if it's not in standard form, you need to put it in standard form so you can see which is your leading term. The coefficient in front of the term with the greatest exponent is your leading coefficient. So a subscript n would be the leading coefficient. The shape is determined by the degree and the leading coefficient. Okay? So whatever the degree is and the sign of your leading coefficient is going to determine your end behavior and the shape of your graph. Okay, let's look at some functions. All right, so our constant polynomial function is f of x equals a, where a is just a constant. Its degree is 0. It has a maximum number of zeros of 0. There are no x-intercepts or solutions. Right? Doesn't cross the x-axis. Linear polynomial function, f of x equals mx plus b, has one intercept, its degree 1, and it has a maximum number of 1, 0. And it will always have 1, 0. Okay? There's no such thing as a linear function that doesn't eventually cross the x-axis. Quadratic polynomial functions, right? So ax squared plus bx plus c is degree 2. The maximum number of zeros, is 2. However, it can have 0, 1, or 2 x-intercepts. We'll have 0 x-intercepts if our x-intercepts are complex solutions. So we have an I, right? We're not going to cross the x-axis. If we have 1 x-intercept, it's going to be our vertex. Otherwise, we'll have 2 x-intercepts. But we always have 2 solutions. It's just sometimes our solutions aren't x-intercepts. And moving along, we have the cubic polynomial functions. ax cubed plus bx squared plus cx plus d is a third degree polynomial. The maximum number of zeros it can have is 3. However, it can have 1, 2, or 3. It's going to have 1 x-intercept, and this is listed over here. It's going to have 1 x-intercept, and if it has 2 complex. Right? So we have to have 3 solutions. So if we only have 1 x-intercept, then you're going to have 2 complex solutions. Or you could have 1 x-intercept with a multiplicity of 3. Meaning you have 3 of the same factor. Okay? So for instance, the graph y equals x cubed, we set that equal to 0. 0 equals x cubed. Right? Well, I take the cube root of 0, and I'm going to get 0. This one would count for 3. So this would be multiplicity 3. So our power functions that go through the x-axis through the x-axis, y-axis, through the origin, and have no other terms with it, are going to have only one solution, and it's going to be multiplicity, whatever the degree is. So that would be multiplicity 3 for y equals x cubed. So you can have just one solution and the other 2 be the same thing and have multiplicity 3. You could have 2 x-intercepts if 1 is repeated. So that means one of them has multiplicity 2 and one has multiplicity 1. Or you can have 3 x-intercepts if the multiplicity is all different. Polynomial end behavior, consider what happens. Oh, I don't think I finished reading that page, excuse me. we got to talking about the cubic, and then I completely forgot because I wrote on the bottom there to talk about the quartic. So quartic polynomial functions, f of x equals a x to the fourth plus bx cubed plus cx squared plus dx plus e. So that last thing without the last term, like the d and the e without an x, is just going to be a constant term. Its degree is 4. Maximum number of zeros is 4, but we can have 0, 2, or 4 x-intercepts. And actually, we can have 0. I'm going to change this. Let me see if there's any way. Could we have 3? If 1 is, no. Yes. So technically, I'm going to change this here. If we have 0 x-intercepts, we have 4 complex solutions. If we have 1 x-intercept, then either we have multiplicity 4, like y equals x to the fourth. It would have 1 0 at 1. Its only x-intercept is at 0, and occurs 4 times because it would be x to the fourth equals 0. It could have also 1 repeated, and it can't have 3. So it could have 1, no, that's it. That's the only way. The only way to have 1 x-intercept is, oh no, there's one other way. So if I have 1 with multiplicity 2, and I have 2 complex, that would be the other way to have only 1 x-intercept. I could have 2 x-intercepts, and it might be that they have multiplicity 2. Each one of them has multiplicity 2. It could be that I have two with multiplicity 1 and 2 complex. That would also give me 2 x-intercepts. So 3, if I have 1 with multiplicity 2 and 2 with multiplicity 1, that would give me 3. Or I could have 4 x-intercepts if they all have multiplicity 1. All right, so there's our different combinations of 1, 2, 3, or 4 x-intercepts. But there's always 4 solutions. Okay? So that's how they could break down. All right, so now end behavior. So polynomial end behavior, we're considering what happens when x gets very large in positive and negative directions. It's called end behavior or long run behavior, and basically the leading term, a n to the xn, dominates the shape of the graph. There are 4 possible scenarios, right? And so y goes to infinity as, that thing is supposed to say as x goes to infinity. So I'm going to write that a little bit larger. It's so small. Y goes to infinity as x goes to, oh, there it is. It's right below. That thing says as. All right, so y or f of x goes to infinity as x goes to negative infinity, and or f of x goes to infinity as x goes to infinity. So regardless of what x is doing, y goes to infinity on both ends, and that's going to happen if our leading coefficient is positive and the degree is even. Okay, so these are our the two on the left here are the even shapes. There's only 4 basic shapes. There's the 2 for the even and there's the 2 for the odd. If instead the leading coefficient is negative, then we're going to have y or f of x goes to negative infinity as x goes to negative infinity, and y or f of x goes to negative infinity as x goes to infinity. So regardless of what x is doing, y is going to go to negative infinity. With our, if our leading coefficient is negative. With our even degree functions, right, the ends go the same direction. So ends go the same direction. They either both go up or they both go down. If it's positive leading coefficient, they both go up. If it's negative leading coefficient, they both go down. All right, so here if we have an odd degree, for odd degree the ends go in opposite directions. All right, so our leading coefficient is positive in the first one. Leading coefficient is negative in the second one. So if our leading coefficient is positive, we go up left to right. If our leading coefficient is negative, we go down left to right. Right, and the end behavior, y goes to infinity as x goes to infinity. Whoops, how did that happen? My page just turned. I don't know if I hit something? I don't know. I must have hit something. So y, or f of x, goes to infinity as x goes to infinity, and y, or f of x, goes to negative infinity as x goes to negative infinity. Usually we start with the negative infinity side. I had read the positive infinity side first. So f of x goes to, y, or f of x goes to negative infinity as x goes to negative infinity. Y goes to positive infinity as x goes to positive infinity. So they're both going the same direction when in other words, the x and y go the same direction. They both go to the negative, they both go to the positive when your leading coefficient is positive. And that's because if you, for instance, cube a negative number, I'm going to get negative. If I cube a positive number, I'm going to get positive. So the sign of x and y are going to be the same. However, if you have a negative in front, the sign of x and y are going to be the opposite. So our graph will go down left to right, and y, or f of x, will go to negative infinity as x goes to infinity, and y, or f of x, will go to infinity as x goes to negative infinity. Right? So our graph is going to go to infinity as x goes to negative infinity, and it's going to go to negative infinity as x goes to infinity. Okay? They're opposite one another, because if I cube a negative number, I'm going to get a negative, but if I multiply it by another negative, I'm going to get a positive. Okay? That's why they're going opposite directions. All right, just waiting for the page. Okay, so turning points of a polynomial. A turning point of a function is a point where the graph of a function changes from sloping downwards to sloping upwards, or vice versa. So the gradient changes from negative to positive, or from positive to negative. Generally speaking, curves of degree n can have up to n minus 1 turning points. For instance, a quadratic has only one turning point, and we call that the vertex. A cubic function, I'm going to write vertex in there. A cubic function can have up to 2 turning points. So it would look something like the graph to the second graph there. However, some cubics have fewer turning points. For example, f of x equals x cubed. It has no turning point. Has no turning point. However, but no cubic function has more than 2 turning points. In the same way, a quartic could have up to 3 turning points, and so it would look something like the graph on the left there, or the right there. But again, some would have fewer turning points, but none has more. Okay, so you can have, we can have a, for instance, f of x equals x to the 4th looks something like this. All right, it also has 1 turning point. But if I have more terms than just x to the 4th, I'll look a little bit W-shaped, and I can have up to 3 turning points. Okay? So it depends on how many terms I have with the leading term. So key ideas: you can sketch the graph of a polynomial function using the x-intercepts, the y-intercept, the degree of the function, the sign of the leading coefficient, and we're also going to be estimating turning points. The x-intercepts of the graph of polynomial function are the roots of the corresponding polynomial function. Right? In other words, once you have it solved, you set factors equal to 0 and solve for x. When a polynomial function is in factored form, you can determine the zeros from the factors. When it's not in factor form, you can use the factor theorem or remainder rational root test. To determine the factors. When a factor is repeated n times, the corresponding zero has multiplicity n. The shape of a graph close to a zero of x equals a, multiplicity n, is similar to the shape of a graph of a function with degree equal to n of the form y equals x minus an. So for example, if we have multiplicity 1, multiplicity 3 looks an awful lot alike. So here we have the blue, the red graph there is y equals x minus 1 cubed. So notice it looks a lot like y equals x cubed. It's just shifted 1 to the right. So polynomial functions change signs as x-intercepts that correspond to zeros of odd multiplicity. So if we have an even multiplicity, we're just going to touch and turn back the other way, so we're not going to change signs. But if we have an odd multiplicity, when we cross, we're going to change signs. Polynomial functions do not change sign at x-intercepts that correspond to zeros of even multiplicity. The graph touches but does not cross the x-axis at these intercepts. The graph of a polynomial, so we can, the last thing I'm going to say is we can graph polynomial functions using transformations. However, we can only do it if it's in this kind of format. So sometimes we could factor it into that kind of format and we could use transformations, but a lot of the times we can't. So some equations aren't written to be written in that format. So instead of trying to get into that format, unless we're given an equation that's already in that format, we're just going to graph by finding those key features. And that's the end of my podcast. All right, so tomorrow we'll do the whiteboard practice. If there's anything, I'll post this lesson after tomorrow, and so if there's anything you want from the review at the end here, you can always print it out. And if you have questions, just ask me in class. Have a great day. Bye.